Up to this time, we've looked at the solubility of salts as they would be dissolved in water. The salt, perhaps sodium chloride, as the solute, the solvent water. And we found that salts generally were quite soluble in water, meaning quite a lot of the salt, the solute, would dissolve in water. Today, we're going to look at gases and how they dissolve in water as well. I like to think of this as simply at the surface. At the surface of what? At the surface of the water, which is considered to be the solvent in this case. And what's dissolving? Well, we're going to consider air as the solute. But as you know, air is a mixture. Air is a mixture of several different gases, and we're going to consider three of them here today. The by far largest component present in air is nitrogen gas. We also, of course, have oxygen gas. And there's a bit of carbon dioxide present as well. And so here we have acknowledged at least the nitrogen, the oxygen, and the carbon dioxide that would be present in the air above the water solvent. Now, these are gas phase molecules, and as such, they have a lot of translational energy, and in fact, they're moving around with great speeds, and we can imagine that this nitrogen molecule might actually be moving in the direction of a collision course with the water solvent below. Now, at the surface, one of two different things can happen. It might be that the nitrogen molecule is deflected off in a different direction. It might also be that the nitrogen molecule penetrates the surface and becomes a nitrogen molecule in an aqueous environment. All right. The same things can happen with the oxygen. The oxygen molecule may be deflected off. It may also penetrate into the surface and become an aqueous species. And the carbon dioxide, of course, can do the same thing. Now, not all molecules, of course, are aimed in the correct direction to become aqueous species. Some may be moving in just the wrong direction. Gas phase species are moving in all directions at incredible speeds. Some of them will penetrate the surface, and others won't. But there's another factor that we need to consider here, and that is something that we learned when we looked at aqueous solids, or solids dissolving in an aqueous environment, and that is this notion that like dissolves like. And we acknowledge, in fact, that the water, in this case, as has always been the case, is a polar solvent. And we know that the one way we have of optimizing what dissolves in water is to match it with something that is a polar solute. Unfortunately, in this case, all three gas species are in fact nonpolar. That's right. Nitrogen, oxygen, and carbon dioxide are all linear and have no dipole moment and therefore are nonpolar species. This is an example of what happens when you don't have like dissolves like. And in fact, only a few of the N2, O2, and CO2 molecules accumulate. By far, most of these molecules will wind up returning to the gas phase with only a few lucky ones, dissolving in the water solvent. And therefore, we don't really see the concentration of nitrogen, oxygen, and carbon dioxide. The concentrations of these gases in the water solvent rise to a very large extent. Now, there are situations, however, where we would like to dissolve a gas in a solvent like water. And the question is, well, what can we do? How can we get more of the gas to dissolve in the water? Well, there is a way to do this. If we return again to our water-gas interface, where we have the water down below, and we have the gas above. And in this case, what we're going to do is we're going to focus our attention just on the carbon dioxide molecules, because they have an interesting application we'll get to in just a moment. Now, these carbon dioxide molecules, we know, as all gas molecules are moving with great velocity, and we have the same situation where there'll be a choice to be made, and some of the gas phase carbon dioxide molecules may enter into the water solvent, but most of them won't because of this problem in that they are nonpolar, whereas the water is polar. So how can we get more of them to dissolve? Well, it turns out brute force is the solution. All we have to do is increase the number of carbon dioxide molecules that exist in the gas phase increase their numbers a lot, making it more likely that the gas phase carbon dioxide molecules will actually penetrate the surface and will therefore become dissolved in the solvent. And so the brute force approach is simply to increase the number of carbon dioxides in the gas phase. Now, what we've done in terms of the ideal gas law, PV is equal to nRT. What we've done by increasing the number of gas phase molecules, we've done nothing to R. R is a constant. We'll assume the temperature hasn't changed, and we'll assume the volume of the container hasn't changed either. But if we've increased N, the number of gas phase carbon dioxide molecules, why, we have also increased the pressure. We've increased the pressure of the carbon dioxide, which consequently increases the number of carbon dioxide molecules above the water, which increases the likelihood that some of them will dissolve. And so let's sum this up in the following way. We increase the pressure of the carbon dioxide, which produces an increase in the number of carbon dioxide molecules present in the gas phase, which then increases the number of CO2s in the water. Just because there are so many more colliding with the water, there's a greater likelihood that some of them will actually stay in the water. And so by controlling the pressure of the carbon dioxide above the surface of the water, why, we can increase and control the number of carbon dioxides that are present in the water phase below. Now, how is this done in actual practice? Well, off to the right, I have a diagram here for you. The beverage in this case is in a 2-liter bottle, and the 2-liter bottle is about 2/3 of the way full. Now, this is a beverage that one would consider to be flat, uncarbonated, and our goal in this little experiment is to carbonate this beverage, which is something that we can actually do. How do we carbonate the beverage? Well, what we would like to do is we would like to get a lot of carbon dioxide dissolved in the container below, in the liquid below. How do we do that? Well, from the lesson we've just learned, we need to increase the pressure and increase the number of carbon dioxide molecules in the gas phase above the liquid. We need to make this ever more crowded. Now, the way we can do that is by using high-pressure carbon dioxide in the gas cylinder at left. And what we do is we connect a hose, and this is something that can actually be done. We connect a hose that will transport the carbon dioxide from the high-pressure tank into the space above the 2-liter bottle. And what we do is we create a high-pressure carbon dioxide situation in the space above the liquid. High pressure to the tune of about 3.5 atmospheres. That's a lot of carbon dioxide. And by increasing the amount of carbon dioxide in the space above the liquid, we increase the likelihood that there will be carbon dioxides penetrating the liquid and staying in the liquid, thus carbonating the beverage. And so what we would say then is, after the carbon dioxides, enough of them have entered into the solution down below, into that solution we're going to drink, we would refer to this as simply carbonation. So we've carbonated the beverage in the bottle below by using high pressure carbon dioxide to make this happen, and the beverage is carbonated. Okay, well, as you can see, the amount of carbon dioxide that actually stays dissolved in the liquid depends upon the pressure of the gas phase carbon dioxide above the surface of the liquid. And this result is known as Henry's law. Henry's law tells us that the solubility of the gas in the liquid solvent is proportional to the pressure of the gas. The higher the pressure, the higher the solubility. That's the way a proportionality works. And I have that diagram for you in this little equation down below, where this symbol right here means proportional. Where the solubility of carbon dioxide is proportional to the pressure of the carbon dioxide present in the space above the liquid for the gas. And so the solubility refers to the solution and how much carbon dioxide is actually dissolved in the solution, and the pressure refers to the gas pressure above the solution. Now, we can actually sum this up mathematically, as all proportionalities can, and I'll refer to this in the carbon dioxide example that we're looking at above. The solubility of carbon dioxide in the liquid, I'll replace the proportionality sign now by an equals, and I'll include a constant that we'll get to in just a moment. This is the proportionality constant, and then we have the pressure of the carbon dioxide in the space above the liquid. This proportionality constant is known as the Henry's law. The Henry's law gas constant. And the Henry's law gas constant is a constant that does depend upon the identification of the solvent and the identification of the solute, and it's something that we would look for in tables. These are extensive tables for all different combinations of solutes and solvents, and your book has many examples of this. Now, for the record, the Henry's law, gas law constant for carbon dioxide, which we'll use here in just a moment, has a value of 3.4 times 10 to the minus 2 molarity per atmosphere. The units on the Henry's law gas law constant tell us that the pressures that we work with had better be in atmosphere units, and that what comes out is a solubility in molarity units. The Henry's law equation works with atmospheres in terms of pressures and solubilities and molarities. An example, I think, will help demonstrate how one uses Henry's law to determine some rather interesting characteristics of the soda that we just talked about. In this example, we're considering an unopened 2-liter bottle of soda that is pressurized with carbon dioxide to the tune of 3.5 atmospheres. In the picture down below, I have an unopened bottle, and I'm going to draw an arrow here to indicate that the pressure of the gas in that little space above the liquid is actually equal to 3.5 ATMs, 3.5 atmospheres. That's the pressure of the carbon dioxide that's present in that space right above the liquid. And for that matter, it's a rather high pressure. Remember, atmospheric pressure is 1 atmosphere. We're talking about something 3.5 times larger than atmospheric pressure. And that, folks, is why the bottles are so stiff when you buy them in the store. If they were squishy, you'd know that somebody had let all of the carbon dioxide out, and I would recommend you leave that one on the shelf, or better yet, return it to the store owner, because it's obviously defective. Now, the question is, what is the molar concentration of the carbon dioxide dissolved in this beverage container before it's opened and hours after it's opened? And that's what I have over here on the right. You can see that in this particular case, the cap is gone, and we'll have to consider a different set of circumstances as we determine how much carbon dioxide has actually been dissolved in that case. All right, so let's take a look at this new bottle, a new unopened bottle of beverage that we're going to determine we're going to determine how much carbon dioxide has actually been dissolved in this container. So, let's see. Henry's law tells us that the solubility of the carbon dioxide is equal to the Henry's law constant for carbon dioxide, which we were given previously, times the pressure of the carbon dioxide that is present in the space above the solution. All right, now we've got all of the numbers we need here. We've got 3.4, this is the Henry's law constant, times 10 to the minus 2. I'll include the units here, molarity per atmospheres. And then we need to multiply by the pressure, which was 3.5 atmospheres. That's the gas pressure above. And while we're at it, let's just see how these units work out. Atmospheres on the bottom here cancel with atmospheres on the top there. So we're going to get an answer in molarity units. We'll actually get the concentration of carbon dioxide in units of moles per liter. We do the calculation. And the result that we get is 0.119 molar. All right, this is the actual concentration of CO2 in the beverage. And it's a rather high concentration. The reason it's so high is because the pressure of carbon dioxide above the solution is so high. It wouldn't be that high if the pressure were something less than 3.5 atmospheres. One would consider this to be a fairly high concentration of carbon dioxide, but what happens when we open the bottle? Well, referring to the diagram at right, when you open the bottle, a burst of carbon dioxide leaves the bottle, and because it's at much higher pressure than the atmospheric pressure surrounding it. And so what we have when we open the bottle is the pressure of the atmosphere, which we'll assume is simply 1.0 atmospheres. Okay? Now, so you open the bottle and you hear that hissing sound as the excess carbon dioxide leaves the bottle, and you might even think that, well, certainly the pressure of carbon dioxide now in the space above the liquid has gone down, and indeed it has. But you can't assume that the pressure of the carbon dioxide is 1 atmosphere, and that's because carbon dioxide makes up such a very small part of the air that we breathe. Most of what we breathe is nitrogen. Most of that 1 atmosphere's pressure is that due to nitrogen. What we actually need is something called the partial pressure of carbon dioxide in the atmosphere. And the partial pressure, which is in effect the pressure just due to the carbon dioxide, is actually a very small number, 0.000385 atmospheres. And so by opening up the bottle to the atmosphere, not only have we reduced the carbon dioxide pressures, but we've reduced them very significantly from what was 3.5 atmospheres to now 0.000385 atmospheres, a very low pressure indeed. And we can calculate now the solubility of carbon dioxide in the same way that we did when we calculated it for the unknown or for the unopened bottle. Okay? The numbers, though, are quite a bit different. We've still got the same 3.4 times 10 to the minus 2. This is the Henry's gas law constant in units of molarity per atmospheres. But now, the pressure of the carbon dioxide for this open bottle of soda, we have 0.000385 atmospheres. Well, the units do cancel out the same way as they did before and leave us with molarity units in my final answer. And if I do the calculation, the solubility of carbon dioxide in this case comes out to be 0.0000131 molar. Now, this is about a 10,000-fold decrease in the amount of carbon dioxide that was dissolved in the beverage. And so the solubility of carbon dioxide, without all of that high-pressure carbon dioxide above the liquid, goes down by a factor of about 10,000. Now, solubility, recall, is the amount of carbon dioxide that can dissolve under those specific conditions. And by simply opening up the cap, we've decreased the solubility of carbon dioxide in this soda. That is to say that a lot less carbon dioxide should dissolve once the bottle is opened. And we observe this? We observe this very easily, very simply. When that bottle opens, we see bubbles rise to the surface and release their carbon dioxide to the outside atmosphere. Why? Because more carbon dioxide is dissolved in that solution than should be, by about a factor of 10,000. Therefore, what happens is the excess carbon dioxide that under these conditions shouldn't be dissolved is released into the atmosphere, and the soda goes flat. Well, that brings to mind the last question having to do with gases and solubilities. How does pop, or soda, go flat? We've discovered one explanation. If you open the bottle to the atmosphere, what you do is you decrease the pressure of the carbon dioxide in the space above the liquid. Now, a decrease in carbon dioxide pressure also decreases the solubility of the carbon dioxide. And as a result of this, less solubility means less carbon dioxide can be dissolved, and therefore the excess carbon dioxide that is in the solution but not supposed to be there, it's in effect supersaturated, the excess carbon dioxide is released to the surroundings. And as that carbon dioxide is released into the surroundings, the soda that we were looking forward to drinking loses its fizz, so to speak. Well, how can you get around this? How can you keep a bottle of pop from going flat? Just keep the bottle cap on. Let the pressures increase in that space above the solution to levels that will keep the carbon dioxide dissolved in the soda, which is where you want it. Well, there's also a second reason pop can go flat. The second reason has to do with the solubility of carbon dioxide and how it depends upon temperature. In fact, the solubility-temperature relationship is quite important, as it's very different from what we've seen in the past. Recall that in the past we've observed solubility curves that told us that for solids anyway, most solids, their solubilities will increase with temperature. As temperature increases, sodium chloride dissolves in water better and better with increasing solubility. However, for gases, it's a different trend. As we increase the temperature, the solubility actually drops. At low temperatures, we observe high solubility, and at high temperatures, we observe low solubility. This is just the opposite of what was observed for solids dissolving in liquids, solids dissolving in water. If you want a solid, most solids anyway, if you want more to dissolve in the water than you had before, increase the temperature. More will dissolve. But that's not the case for gases. For gases, increasing the temperature actually decreases the solubility. And this is the situation for carbon dioxide. We would like as much gas as possible dissolved in the liquid, and we'd like it to stay there. We'll keep the bottle cap on to help with this. However, if the beverage is out in the open and you want it to, and the bottle is open, and you want that carbon dioxide to stay dissolved in the liquid in the beverage, what you want are low temperatures. For low temperatures, we know that we have high solubilities. And high solubilities tell us that a lot of carbon dioxide, in this case, is actually dissolved in the water or in the beverage. So there you have it, the complete and total story on how to avoid a beverage going flat. The first thing to do is to make sure that you put the cap on the bottle and don't release any of that carbon dioxide. Let it pressurize, and the release of carbon dioxide from the beverage will decrease. And the second is to recognize that the solubility of carbon dioxide is greatest when the temperature is low. And so by keeping that beverage low, we can actually keep as much as possible the carbon dioxide dissolved in the beverage, which is where we want it.